Hi, we'll just wait for a few minutes and then start. In the meantime, if you guys have any questions, you can ask. Okay, yeah. So the question on recap on exception handling. Okay. Um, honestly, like I was saying, there is the try and accept forms, which I think my screen is visible. Okay, yeah. So the try and accept forms where you assert a condition and try to catch if that fails or something like that, right? So that's essentially the idea. C++ does give um, this functionality to perform these operations. Now, uh, there are various kinds of errors that one can encounter. Again, what I suggest is look through the documentation of C++. There you'll have the most up-to-date features and all. So you'll get the most detailed try and catch errors, as in the exception handling cases. So that's more or less it. I'll maybe recall what we covered last week. So yeah, and then we can today get to some more interesting topics. All right. So yeah. All right. Yes. So we saw about templates last time, like previous week, right? So templates useful in the sense you don't have to repeat code, and especially useful for when you have the same code for different data types for inputs and outputs and so on. Okay. Similarly, you can extend the same concept and idea to class templates. So your class itself can have a templatized parameter which templates the whole class, right? And yeah, sometimes the uh, functions, okay, can also, or methods that you call, can be in sort of can infer the type or template. So we saw some examples that there also. Okay. Uh, yeah, like sort. Yeah, like here. You do not need to. So max is a function, but here you do not need to explicitly pass the template. It sort of infers from the input types and returns it also. Okay. So that's more or less it. And This was a macro using the same idea, but again, macros can have various problems, right? It's a preprocessor directive. So before compilation happens, macros get processed. So you might run into issues and errors that you can't even exactly debug through compiler errors, right? So yeah, right. So that and then this, okay. We saw class templates. Initialize a class initialize a class object and then call the corresponding function of it. Okay. Similarly, you can have min function, max function, and so on. Right. So that's that. The other template was with respect to the vectors. So like this is standard vector is a v, which takes value and to resize it. Okay. Where the object is known, but the vector to it is not, like you don't exactly have access to it because it's private. So things like that. And then how do you play around with it? Something like this you encounter when there's an external header file, which let's say takes multiplies two matrices. It just takes the input of those two matrices and then gives you the output. While the body of it is hidden. So in things like that, we can have a templatized class also, and then the object is sort of like hidden to it. Yeah, those kind of things. Then yeah, overloading operators. So the equal to operator here is overloaded, right? And the other case we see is the dereference operator accessing the ith value in A sort of overloads the bracket operator and sort of like returns the pointer. It does a pointer arithmetic in the starting position of the sorry, 1 second. Yeah, okay. So from the starting position of A, you have ith units and how much bytes it has to move. It automatically knows from the size of like what is that pointer itself. Here it's an integer pointer, so it knows how many bytes it has to move. After that, a dereference, and then you sort of like it returns this, right? So accessing the ith value at some vector essentially means this, and here the bracket operator is sort of like overloaded. That's another example. Then yeah, input output. So we saw about how IO is handled. We have been printing stuff, so that's also the starting point of how input and output is handled in C++. We need the IO stream header file to access the cin, where it takes in values from the terminal. So always remember, in or out is with respect to your code itself. The code is the reference. Okay. So input will be input to your code. Output will be output from the code. Okay. So input to the code is C. So it takes some values from the terminal, whatever the user gives. And then there's a print statement from the for the hello world that we are giving to the output as an output. So the cout sort of accepts a stream of uh, bits. Here it happens to be a string of characters, so it knows what to print. Okay, and this operator is overloaded. It accepts integers, strings, and all these default data types. It knows how to handle them. So it prints all those values accordingly. Okay, and then we sort of see what's the role of standard END. So standard endline essentially is the sort of like a fusion between standard flush. So flush is basically clearing the buffer, and slash n is essentially a new line addition. So if you want a new line, you can add this, but with standard end line, as there's an additional effect which is clearing a buffer. So the strings and all the stream of bits to the stream of cout or cin both, they're stored in sort of a buffer first, and when that buffer uh, I mean, it depends on cases when it gets flushed. but you can enforce to flush so as to print them, okay, uh, with just standard flush or use the standard inline. Okay. Now, moving on. So a simple example of using uh, IOStream is the two functions in IOStream, like C in and C out. The other useful thing to do is manipulate these streams. So hence we require the IO manip header file. Okay. So in that, we take this example where we have an integer I, which is 17. We have a hexadecimal long. Okay. We have a long unsigned int I64. Okay. So this is the hex representation of that. So these are some very large numbers that you can represent in. I think this was in 32-bit and this is in 64-bit. Okay. Large integers, I mean. Then you have the float f, which stores the same output, 15 divided by 7. Okay. In both float and double. So FP32 representation and FP64 representation. Okay. Then we have a C, which is character, stores just X, and then a pointer character S. So it's a const character, as in we don't want to change it. So it's a const character pointer. So S points to a string of characters which has the word Aman. Okay. Next, we have an address S that we take to see what's the actual address here. So it will store the long unsigned int. So that's what I'm casting it to. Okay. As pointer and then S. So S will uh, have a S is a pointer, so it will have an address. So we can cast it and then try to read off of it what is actually mean. What is it actually storing? Okay. And another integer pointer P. So that stores the address of I, which is this guy. Then we start printing all the stuff where first of all we see I print. Okay. Then the hex of I. So this will actually print the hexadecimal form of I because I is if just numbers are returned, it's by default decimal. Okay, unless you give 0, D and on so on. So because of this representation, it it in it in, infers that it is in hex. Okay, so you can have standard hex given and then print I, which is 17 in hex form, and then again in oct form. Okay, then we try to print L and I64. Okay, so they will be represented in the decimal forms because that's the default behavior. You give hex numbers, then default will be to represent them in decimals. The next is, okay, maybe I can run this again and then see. Sorry for that. Okay. Should have 10 here. I mean, okay. Yes, yes, here. All right. So what we do is run this file to data. Okay. All right. So what we see here is at first, right? So the all these things we discussed now. The next is representing. So F and D are essentially some floating point numbers. Okay, but the difference is how many bits they're used to represent the same number. So 15 by 7 theoretically has infinite digits. Okay, so um, a float will store only the same number using 32 bits with some rule of representation, and double D will store in the same number in 64 bits. So to see how much precise each representation is, we can set the number of precision or decimal points it actually prints. Okay, so using the set precision. So 16 says still 16 decimals you print. Okay, so F prints this and D prints this. So if you see, a lot of these digits are common, and then it starts deviating. So the reason for that is, again, there are only finitely many digits, bits in a computer, and you can store only a finite precision of them. Okay. Yeah, exactly. Precision hierarchy. So that's why you see the difference. You can trust that the D value will be more accurate because it will naturally, it is 64 bits, so it will have more accurate bits. Okay. But even D has its limitations. After certain digits, you can't really trust it. Okay. So that comes like, so if you take a relative error between the actual value and this, so you can be sure that if you get 10 power minus 15, 16, then you're good. Okay. All right. So see the character, that's what it prints even for S. Here it sort of knows where to end actually. It's the character pointer, yes, but sort of knows where to end. So it does that. And then we try to print the address of S, so through this, and the address voids using a void star. Okay. So this is the S. Address of S means the address of the actual pointer where it is stored. So S is the pointer. Itself stores an address, yes, but that pointer also is stored in some address. Yeah, something like that. There is a end condition always, that like will come to the file I also. Essentially, there is always a end of line, end of start of line. There are special characters which determine how much where the end of anything is. It's actually there, but by default, to make text as like this, a code of text from what we're seeing here to be more readable, those things are usually hidden. Yeah, but that's correct. So if you see LF here, that means this is a select, this is an end of line sequence. So EOL, it's called EOL. LF is for usually Linux type systems. CRLF is for Windows, and I think CR is for Mac. Essentially, there are three, like there's a combination of it. But it is different for each uh, OS. Yeah. Then, yeah, so S is the address that we see for S. So that's the ampersand S. And address of S itself, which what it stores, we see here. That's what we're storing. Okay. And that is the same as if you just cast it as a void pointer and try to print it. Okay. All right. And then P is just address of I. Okay. Um, Then we saw this example, okay, where looks a little complicated at first, but we try to break it down and see that we're actually trying to overload this um, bitwise shift operator. Essentially, what we use this, where we use this is in the specifically, we'll take the case of standard cout. Okay, so what we're doing is we're making it a friend function. Okay, then what happens is uh, outside the class, functions can have access to it, or outside classes, objects, whatever you can think of. So the outside class which we wanted to have access is actually standard cout. Okay. Normally, when we have this operator with standard cout, it is overloaded only for the inbuilt data types, integer, float, characters, those kind of stuff. But here we have a custom class of complex. Okay. And let's say I want to simplify it so that I do not want to write, if I want to print a complex number like C1, I just wanted to pass it like a simple number to standard cout. So let's say this is the goal of the problem. Okay. So sort of don't have to write this again and again. That is one. Second thing is sometimes you cannot even write this because you do not have access to the real and imaginary part separately for that complex number. Let's say for somehow we don't. Um, Also, it makes the code cleaner in that sense. So hence all the stuff is put inside here. Here this operator, which is shift operator. returns a type of standard O stream. O stream is the output stream. That's what we're working with. Okay. As Cout has a output stream, returns as a reference. Okay. So that's the reason is you don't want to copy. You want the exact string to get added and modified. Okay. So that's the OS stream it takes in. So here this operator, okay, has C1, this colon with a space character, C2 also. So all this, uh, since we separate them by this operator, each of them gets a new OS. So that's the OS here for this guy. The OS is C1. Okay, right. So and the complex number C1 also it takes. So here so far the output stream did not have anything, so it's like sort of like null. In for this guy already the stream contains C1. That's what we are saying here, and it adds the this characters. So essentially the idea is that you want to write it so that it doesn't break for any new for any existing data type, and you're adding on top of it, and you're adding your uh, case on top of it. Okay, takes a complex number. So here we only need to worry about the complex number because that's what we're adding. All the rest of it is already overloaded and there inside the standard cout. Okay, takes a complex number, returns again, it adds to the stream. Okay, the bracket, the real number, it puts a comma and puts the imaginary part and closes the bracket. Okay, and then returns that OS, the string. Okay, so here we so then what happens is your uh, operator will only print that number. So let's say we do not return OS. Okay, I mean we can. I don't want to break. Maybe it will throw errors and also I'm going to break it. But you can imagine this way. So we don't return this and then print it. Then try and see actually. It's then has this and I just yeah it actually return experts return type. That is true. Yeah, it will only print. Yeah, okay. You can think this way. It will only print the C, the complex number. That's it. You can't chain it further and further. That's essentially the limitation. Yeah, I think we did see it last time somehow. Yeah. And then do else. Changing any of this will make it a different function itself. Mm. Microphone error, but yes. Yeah, can't have the other type. Anyway, I hope the idea is sort of at least clear from this that we sort of want to chain with different arrow the shift operators. If we do not return it or do not have this OS, the only reason I'm not changing this is because the operator will then actually throw errors. So it actually sort of because we're overloading it, it sort of expects certain parameters. Okay. So anyway, the point is having just this and not returning it will only print that C1 and the chaining of more and more outputs like in this way will fail. Essentially, that's the problem. Then right here we see the file IO for the input and output for files. So for that we iStream is there, sure, but we need some header file called xstream. Yeah, okay. Question. Returning a private class. Um, that's okay in the sense sometimes we want to know, let's say we're actually, let's say here printing the value in the sense we don't have access to it directly, but sometimes you still write getter and setter functions, right? It's sort of like similar there, that way. But we're not writing a getter or setter function. Usually one writes getter or setter function to change or get the internal member variable where we don't have access. If you're returning it, you can override it. No, you can't. You can't change that value directly, but it's just a return, as in it's just a copy of that value. You're not exactly going and overwriting it. You sort of does know, you do know the what value it contains, but not the change. You can't change it because we don't have access to it. Okay, it's sort of read only. Yeah, that also is not exactly correct because read only is something more like if something is const. Here it's like we have access to the value, but we can't change it in that sense. Yeah. Let's say the private member is itself const. The class itself also cannot change it. Let's say it is const in that sense. Yeah. But in the previous example we saw, it is not const, but the class can change its values. So technically speaking, if there is a function, let's say I have not written anything, but let's say we add some more functions which change the real and imaginary part, let's say. So C1 will have different real and imaginary values. This standard cout will still work because we're accessing the values of the real and imaginary for this complex number, but we won't be the ones changing it, as in from outside the class. Maybe some function inside the class will do, but not us. And I mean, I hope the idea is clear. I mean, there will be some code which we write, but the function or the okay, let's call it function in general for a generic thing. The function which will be changing this will be from inside the class. Okay, that's what I'm getting at. Yeah, in a way, yes, that's correct. Okay, coming to the file IO. So we require a header file called fstream, okay, which has OF string type. So we're creating a my file object, okay, of that. And then this is essentially a file object, and we're saying we'll open that file with this name. So as in, this will create this object is a C++ object, okay, which will create a file with it will have its own handle and say it will we say that its name will be test.txt. Okay. We open the file, it creates the file, okay, and then we start inputting all the stuff to it. So we enter all this text inside the file object. So it automatically starts writing to it, okay. And then finally we close the file. So that's it. So it automatically says that my code which was which took the ownership of this text.txt as in this file is now closed, and any other process is free to start changing it or reading it or whatever. Okay. All right. So that's this creates the file. Okay. And from the same file, let's say we start reading it. Again, we need streams. Okay, streams and file stream. And here now in this case, we'll make an object which is if stream as an input file stream. So this file exists, and that's what we're saying we'll try to read it from. Okay. This is the same directory. You don't need to give the complete path. Otherwise, if just the text name or the file name, so it means the current directory. Okay. We make a line, standard string line, which will take all the each line as an input. Okay. Um, in an iteration, it's like in a loop, and then we start the loop. So first we say check if the file is open, then it doesn't do. It's unable to open the file. Okay, because if it's open, it shouldn't be opening this. But if it's not, then we start the while loop. There's a useful function called getLine, which will go through the my file, text my file as object as the input. Okay, and then each line like we were discussing, right? So each line has a character which says where it ended, as in a line ended. So that line gets input into the string line. Okay. After that is done, we're just printing it to the terminal with standard cout. Okay, that's it. And this happens in a loop until the while loop goes false, which happens when it hits the end of file, or as in the last line. Okay. After this is done and the print is done, we should close the file. Hence the line myfile.close. Okay. All right. I think so far so good. This is essentially what we covered last week. Any questions so far? Okay, awesome. So, all right, let's cover more topics today. The first is this. So, one nice thing about languages like Python is that you do not have to worry about the type. Okay, so makes life a lot easier. You can, let's say, I'll give an example. Uh, Not exactly, it's not exactly similar to T, but um, I'll give an example. So let's say A is some value 5. This is valid code in Python. Okay, is 7.1. So here A is an integer, B is a double, but suddenly you can store this also. It's a list, maybe of integers. That's okay, but still a list. It's not an integer anymore. The data type becomes a list. In Python, all this is allowed. And let's say this is 4.1. You can have mixed types also inside the list. Okay. So all this is allowed and fine. Like you can mix and match types and all. And you do not have to explicitly declare what A is. It automatically inferences what is the type for that A, and then stores or stores objects up accordingly. Okay. So this is a nice uh, feature about with Python. Okay. In C++, yeah, it's a easy life. Yes, you don't have to deal with pointers, but because of this, there's a downside to it. The downside is speed, as in because it's not strongly typed. What I mean by that is the data type of each variable is not known at compilation time. One is that you can't do a lot of optimizations with it. Okay. Second is there is a thing called garbage collection, which kicks in to clear all this data. Okay. So that is a nice feature of Python in the sense you don't have to deallocate memory. So, which is not present in C++. But what we'll now see in today and next few classes, these features, which are very handy in languages like Python, are sort of also available in C++ if you know how to use them. Okay. So in a way, you get the speed which is known for C++, and also using some modern features of C++. Yeah, they are actually in a way. We will discuss these concepts. They're not exactly the same, but you sort of get the same behavior. So one of them is such thing, just auto. Let me give an example. So the usual return, that's fine. Uh, okay, so let's say I write auto x equals to 7. Here, I don't need to, I'm not specifying what the type of x is, like the data type of x is. I'm just saying it is 7 and some auto. And let's say I try to compile this. Do you guys think it will throw an error? As in, what will happen? It will throw an error because it has to be strongly typed and all that. This is, oh, error, sorry, 11. Okay, compile and done. See, it did not actually throw any errors. Okay. The reason you might have seen, okay, this I discussed in first class, but features like this are in modern C++. So you sort of have to give, depends on your compiler. If your compiler already the default behavior is it supports a certain standard of C++, like 17, then you do not need to pass this every time. But just to show that my compiler, okay, it's like your compiler should, if it supports 17, you can always pass this, okay, to enable those features, is what I'm getting at. If it's not default in that version of compiler. Okay, so here I'm passing 17 to enable 17 C plus 17 features, okay, and auto is one of those features, okay, in modern C++, where I'm not sure if it started in 17 or which version, but it's definitely 11 or after. Okay. Anyway, so the point I'm trying to make here is auto is essentially a data type which is inferred. What does that mean is 7 is an integer. So when I write auto x, it automatically takes uh, x to be an integer. Okay. That is the nice thing about auto. You can actually write a lot of this code. Yeah, it's designed by compile time. Yes, that's correct. So one important thing to note here is features like this do not break backwards compatibility, meaning it doesn't change the way C++ is designed or C++ behaves. Like C++ needs all its data type to be all the variables data type to be known at compilation time, which sort of still happens here. Okay. It's just that we're not explicitly writing it. That's all. Yeah. So it doesn't break the design and gives you a nice feature where you can just put auto and be done with it. Okay. Let's uh, see more examples. No, it doesn't. I mean, speed in a way, actually, if you think about it, um, usually compilation is um, quite fast. I mean, unless you have a very huge code base, which then in that case you can't do much. People actually do parallel compilation also. So let's say a lot of processors, you distribute compilation of a huge code base into chunks. And that's sort of the idea behind using Make and CMake and Ninja and all these build tools, where you divide that uh, large code base into different chunks and then process them parallelly and then combine them together. So that is one. And second thing is, yes, I agree that if it does not know, it has to sort of infer. But I think sometimes from readability standpoint and maintainability, it's worth it. It's actually another example I'll give you. So let's say standard map, okay, which is integer. Okay. And let's say this is some uh, map underscore. It's a variable's name. Okay. Now let's say you write the map underscore dot begin. Okay. So this is a iterator. Okay. Um, the way to think about iterator is it's sort of So these are containers. So like standard maps, vector, standard vectors, and all these data structures are sort of like containers. Okay, they contain values. Now, to go over each value, C++ provides a very nice concept which is called iterator. Okay, so we'll cover iterator also this time. Um, yeah, so that iterator, the idea is that as we so it sort of like provides you a tool through which you can access every element inside a container. Okay, it just so happens that because the data is contiguous in layout in a standard vector, dereferencing a pointer, okay, shifting and like accessing the first element pointer, shifting it, and then dereferencing is fine. You can do that. Um, so that behavior is possible and okay because it's a standard vector. There, you know how much shifts happen and everything. Okay, but that is not the same when you have standard maps or sets or unions. Like you can, sorry, not unions. You can perform unions on sets, and you have when you have uh, sets as the data structure, standard set. There, it's just a collection of data. There is no guarantee that all the data will be in contiguous layout. Okay, like the next value will be just after 4 bytes or so on. You can look into more data structures, but what the point I'm trying to make here is for standard vector, the pointer arithmetic and iterator is both are the same because they will go through each data. Iterator will always go through all the data for any container. In standard vector, it just so happens that you can go through each data using pointer and dereferencing. But the same thing won't work if you have more complicated data structures like sets. Okay. So in those cases, to have a generic method, okay, generic functionality to access all the members in a container, C++ provides iterators. Okay. To start with such an iterator, there is a method which is called begin. So map.begin or standard vector.begin and anything object.begin will start the iterator, which looks something like this. Standard map like iterator. Okay. Now let's say you want to uh, like go through like start with this begin and then write it. So you have to give this a data type. So you would have to actually write it this, and then let me call it map begin and store it. So now you can use the map begin to go through each element. Okay, then select like uh, just give me a second. Yeah. So what then you can do is um, increase the iterator. But what I wanted to show is yeah, okay, that's fine. Let's do this way. Okay. So we have to give the data type of the map begin. Start with the begin. Okay. Then until then we put a end condition which will be maybe I'll just call it iterator. Okay. The iterator is of data type this starts with the begin until this is the condition is reached, which is map dot end. So this is the end of that iterator. This ends, then it will stop, and each loop it will iterator plus plus. So iterator will keep incrementing. This is a nice thing about iterator. You do not have to worry about how the iterator is pointing to which value where, but sort of gives an idea. The iterator will keep incrementing each loop, okay, until it reaches the end of the iterator, okay. And here we start at the beginning, okay. And if you see, the loop itself becomes quite huge, okay. So, and then you can do something like this is the, sorry, my bad, iterator, right? So yeah, in maps, what happens is there are iterator has two parts. So you access the first part by using the first, and the second part using second. Okay. So if you see standard map, it has two integers, right? The first part is the first part of that integer. So you can think of them like a set, as in a tuple. Okay. They're like two values together or two somethings together. Here, those two somethings happen to be two integers. Okay. Then you can access them and then start printing. Okay. That's more or less it. Yeah. You can put a comma or something and then, yeah, and then anyway, we can play around with more complicated data structures like this. But the point I'm trying to make here is maybe format it. Yeah. So if you see the um, data type, yes, it is some data type that it should be correct. But honestly, we sort of understand what the um, code here does, and we can avoid writing so all these unnecessary data types. In the sense, we don't need to worry about them. We understand that it's a begin, it's an iterator. Okay, begin will return an iterator. So what we can do is just put an auto here. Similarly, here we just put an auto. Okay, fine. Now here's the nice thing. It makes the code a little more cleaner and sort of at least the idea is still there behind that. It starts with a begin. So we know that it will return an auto iterator, and the data type, however horrible looking it may be, we don't need to worry about it. And the nice thing is it here, it depends. So if you see here, the iterator data type which we wrote before depends on the data type of map also that we actually as in map underscore that we had. So you have to give it integer and integer. Let's say it wasn't the case and it you had to write um, for some other case. Automatically takes care of that. Okay, so that's the neat part. Here it doesn't matter what the data type is. This portion of the code won't change. Okay, all right. That's what I'm trying to get at. The Yeah, awesome. So it's not exactly like T as in templates, but it infers data type in during compilation time like templates. Yes, that's true, but it is more of a declaration type. Yeah. Here I did not use any templates, but I was able to use auto. Okay. You can mix and match. Yes, of course. You can use templates here. You can use the capital T here and sometimes T here also. And in this case, you don't need to put here say iterated. You can just put auto. Okay. As you can see, auto automatically took a very complicated iterator. So there's something like standard map with two integers and then the iterator declaration. Okay. So if we compile this, okay, we compile. Oh, hmm, something happened. Okay. Oh, sorry, my bad. I think I have to include the header file. I think it's inside map. Sorry, let me check. That should be okay. I just did hashing code now. Mm, uh, Sorry, just a second. Oh, you're right. Okay, okay. That's yeah. Here, iterator is sort of like a pointer. My bad. Yes. So you can't use dot, you have to use the arrow. Okay, that's fine. So since it was empty, so it did not print anything. But yeah, if it wasn't, then it would have printed. Okay. Can we use a user-defined class in auto? Mm, yes, you can. So if you think about it, the complicated standard map integer as in two template with some colon iterator is also a sort of a not a inbuilt type. Yes, it was written as part of the standard, but this is not something which is inbuilt, as in simple types like integer, float, and so on. So yes, you can use them. So that's actually a nice benefit of auto. Let's say I write auto. This I'll give an example. Okay, some uh, some data. I'll call it with some return function something. Okay. Now what it returns, as in whatever the function returns, yeah, it won't actually. So that's the thing. If it gets confused, it will throw an error. Yes. But for example, here, huh, okay. So let's say I have an example here, which is function. So I know what the data type return of that function is. Okay. So I can do this auto data equals to function. This is a perfectly valid code because I know the return type. So when it stores the return type into data, it knows and I use auto, it will infer its data type. You can do something like this. Yeah. Let's say your function is the return type of that function is some complicated user defined class. That is also fine. That's also okay. Because if you think about it, standard map integer is also a custom defined class. Okay. Here it could be my function returns uh, my class that we have been seeing before. Let's say that is the data type. So data will also have that data type. Let's say my class reference. We'll return that. Okay. All right. Let's say we do this. Auto y equals to x. We know x data type and y we are setting. So will this be okay? Yeah, that's the thing. Auto is not always used everywhere, as in sometimes it's more important for readability. Sometimes in cases like this, where we sort of know what the intention is, we can avoid writing huge data type by using just auto. Yeah, it can confuse. I'm not disagreeing, but that's why it's one of those again a tool which should be used carefully. And important thing is the developer has to know how to use each of these tools. Okay, not everything will be as in just because it exists does not mean we have to use it also, right? But it's a feature that if used correctly can give a lot of benefit. This is true for every feature, okay, in all the um, new features which are added in C++. So just because it's added does not mean you have to use it, okay? But understanding what it is or what it does can make life simple. And case in point here. Okay, for this example, let's say is fine. Because the data type of y is inferred from x, which itself is inferred from 7. Okay, so comparison time, x's data type is known, so y is also known. Okay, so let's say we do this. Right, so this is, oh, redefinition, sorry, I'll remove this. So what do you guys think will happen? This is fine. Now, important thing to note here is auto does not uh, take const as the data type. Okay, so if you want constness in your data type, you have to explicitly add it. Okay, here auto will take data types like standard map integer integer, or yeah, it will create an error. So no, this is fine. If you what I'm trying to get at is auto does not take constness into account. You have to, it will take integers, it will take doubles, it will take all the, and then all the complicated data types like this, or my class ampersand, like my class reference or whatever. No, reference also you have to sort of give. Okay, so it only takes the data type. So it will here, if x was of type my class, then auto will become my class. Okay, if the return type here was my class ampersand, auto will just become my class. It will not have the ampersand, as in it will not be a reference. To make the reference, you have to explicitly mention auto ampersand data. Okay, so auto does not have the pointers, references. Okay, it doesn't. It doesn't also have constants. We have to actually specify that. Okay, we can also do this. Yeah, we can also do this. We can take this as an integer reference. Okay. Oh, my bad. Not a reference. Let me do the pointer first. Okay, and store the address of it. You can do this. Okay. Let's see the output. Perfectly valid. So we are storing the address of x inside y, which itself we are saying is a const auto pointer. Now the auto is known from the type of x. So x is an integer. Okay. So from that it sort of infers the data type. We can do this also. Const auto. Now I'll have a reference. Okay. But in y. Okay. But instead of x, I'll pass this, the map itself. Y is dependent on X in the sense Y's data type is inferred from X. But what if instead of X I have map? Yeah, if you don't have X, it will throw error. Absolutely, yes. Now, what if I do this? Instead of X, I'll have another variable like map underscore. Then what happens? It's file compiling. That's perfectly valid. Yes. Because map underscore is a is some complicated data type. It's some class, right? Temporarized class. So what I can do is with y, I can make a reference of that same. So auto will basically be this whole thing, okay? In whatever I have highlighted, but it will be const reference, const, it will be const with ampersand, it will be reference. So essentially and map underscore are the same, just with a slight, that's okay. But the point is I can get a reference of also of something. I do not need to specify its type. Okay. If I have auto, so this is some there are some examples of auto. Okay. Now auto sort of infers data type like this. Okay. But let's say I have auto. I'll give the same. Okay. Maybe I'll just copy this. Copy this. Everything is same, okay? But I'll change this name to const and use C begin. So the difference is that begin iterator sort of, you can think of it like the iterator here was not a const, as in it can change the value of the things it is iterating over. A C begin gives a const iterator. Okay, here it looks something like this, const iterator. Okay, now a const iterator cannot change things, but if you see here, the name grows larger and larger. It's a very common thing in C++ where once you start dealing with iterators, the names become too large and it becomes a little hard to read what that code is actually doing. So in those cases, especially, people use auto. Okay, right. So now here, the point is, which one do you mean? Yeah, that's what I'm saying. So keywords like this, right? You actually don't need to worry about them, as in you don't need to worry about remembering. You just need to know that if I have functions like begin and end, okay, they are for iterators. C begin and C end is constant iterators. And for a map, it will look something like this. For another data type, it will look something else. And that's where auto comes in. I don't need to worry about how they look, what I have to declare on. Okay, there will be something. I can just declare auto, start with C begin, store it there, and start iterating. I can just insert this constant here and start writing a loop and so on. That's where the nice, yeah, you don't need to remember what the iterator actual data type of the iterator is. Okay, you don't need to worry about it. Okay. This is a useful thing about auto again, where in C++ you'll have so many kinds of iterators, right? So you don't have to remember them. Auto takes care of all of them. Now here's the important thing. Here I had to put auto specifically because map wasn't an auto, as in this is not const. I had to put const specifically. In this case, auto will be of this data type. This data type has inbuilt constness to it. So this variable will be const, as in behave like a const, because this is a const iterator, as in this data type itself has constness. Okay, remember that. I did not put const here. Okay, does not mean that this map begin is not a constant, as in it won't behave like a constant. Okay, that's what I'm trying to get at. I did not put constness here, so y could change. Okay, a const auto y will make, depending on data type x. So here it will be integer. So auto will be integer, but it will be const. So I can't change y. Here will be const pointer, an integer pointer because of x, but it will be const. Here it will be a reference, an integer reference because of, not sorry, not an integer reference. Again, I have to see the data type here. It will be standard map integer templatized, but a reference. Okay, but again, a const reference to it. So it can't change it, but again, it's a declaration. Okay, that I hope is clear. It is the constness, sorry, the auto type. Okay. Now let's look at another um, example called deckel type. Yes, so here you sort of get the functionality of Python where you do not have to worry about the data type. So that sort of comes in, like just not just Python, some other languages also. So that feature sort of also is available in C++. So technically speaking, you write all the code using auto, more or less. Not here you have to actually declare it. But I would say a lot of the code you can actually write using auto. But then again, the like you asked, question is, should you? Now that's something one has to be careful of, because sometimes you might run, you might in the uh, flow of converting things to auto, you might actually convert something which they might end up with code where it is actually less readable than it was before. So there should be a balance on this. Okay. Let's put iostream, then main, usually return. Let's say I have an integer a and a pointer p. Can declare in one line. It's actually normally people don't recommend to declare pointers and variables in the same line. But if you want to, you can declare it this way. Remember in C++, here integer a, if you declare it this way, it means a is an integer, but for pointers, you have to put the star on the variable itself. If you're writing in one line, as in combining with other variables. Okay. So just be clear of that. Then what I can do is put decal type, okay, on A, okay, and then let's say I declare B. So as in, what does this decal type do? Um, so for example, let's say I want, maybe this will be better to, let's say I type auto B. I want to declare a variable B and I just put auto. Hmm. Will this work? It should throw an error because B is a variable, yes, but we don't say any return type to it or don't set it to anything. The compiler has no idea how to set this value. As in, what is the space it will take? Okay, you can't. So that's what it's saying. It can't reduce the auto. It requires an initializer. Okay, there is no initializer. Yeah, there's no dependencies. There's no initializer, so it can't decide it. But there can be another way to declare B, where we use decal type. So decal type infers the data type of whatever input it gets or takes. A is the variable. We give it decal type. So it infers the data type of A and that acts as the data type with which B will be initialized. Okay. So B will be integer. Okay. The nice thing about decal type is decal type also works with pointers. So P is the integer pointer. Okay. And let's say I declare Q, then Q becomes integer pointer. Okay. Yeah, that's correct. But again, it depends on the code. You might run into some case where, uh, let's say you forgot, or maybe you declared A using auto. Okay. And now you have to declare B and Q, where A and P were declared using auto, or maybe A is this, some function. Right. Then we have no idea what A is. As in, not, I would say no idea. I mean, of course, the code has the idea, but let's say this is in some function I don't want to bother looking at. But I just know that whatever the data type of A is, I want my B and B to be the same, and for Q similarly. That's it. Then Deckel type will just take care of it. Yes. Yeah, we can't use auto. I hope that is clear because maybe put that example also. Okay. I hope this is clear why we can't use auto, but we still want to declare stuff using some pre-known data type, pre-known variable whose data type will probably be known. Yeah. Okay. All right. I think so far so good. I'll give another example, which is the type ID and name. Okay. Um, let's declare A, B, C. Now, there is another um, what you can say is like a functionality in C++. This is called a type ID. Okay. So what it can do is type ID takes a variable like this, and if you choose the name of it, okay, if you call the function name, it returns the data type it has. Okay. Similarly, you can do for B and C. Okay. Did I? Oh yeah, sorry, my bad. There is this type of. Okay. Okay. So if you see the name that from so there will be a type ID sort of a class, you can think that way. It has a function name, okay, which returns I for integer, D for doubles, and F for floats. So knowing the data type explicitly or a variable, also there is a method to it. Okay. So this is one way you can do it. Deckel type takes that uh, data type and you can use it to declare other types. That's the use case here. Auto um, takes the data type, but without the constants or the pointers. Okay. I hope this is also clear. Take another example of decal type. Let's do that. I'll put it. Yeah. Session. I'll include IOStream function. First of all, I have integer a as an integer. Let's say it has 10. Okay. Then integer, let's say my reference to a. Okay. That's fine. Then let's say I have const integer c, which is let's say 11. Okay. Then a const integer reference d, which is taken from c. That is something fine. Oh yeah, that's actually this will summarize it actually. Yeah, that's correct. Okay, so how much? Okay, that's fine. So here the data type is integer. Here the data type is integer reference. Sorry. Here the data type is const integer. And here the data type is const integer reference. Okay. I hope this is fine. Inferring data types of each other. So um, A is a sorry, A is an integer. That's straightforward. B is an integer reference. Okay, so that's what we're writing. Yeah, C is constant integer. So that's what we're saying here. And yeah, that's correct. D is a constant integer reference taken from C. So it points to C. There's a constant integer reference. So these are all the data types. Okay. Now here, now let's take um, examples of examples as such. I'll call it auto C, auto A. Okay, and store A to it, and do it this way. So call it B, call it C, call it D. Essentially, to drive home what each thing will be. Okay. Yeah, that is fine. Actually, if you think about it, let's say A was of type unsigned int. You can still do this line. So it will infer the decal type of A, which was unsigned int, and now B becomes an unsigned int, and we're storing 10 to it, which is perfectly valid. Okay. There could be promotion and demotion of data types. So what we saw before. Yeah, there could be implicit and explicit typecasting. Yes. Only the implicit one. I mean, explicitly also we can do, but we have to explicitly do it. What I'm saying is there can be implicit typecasting. Yes. All right. So what I'm trying to get at here is, what do you guys think? What do you think will be the data type of this? So this is auto A. Okay. To check, let's do the decal type. I don't know if this will work because I don't know if I can print it, but let's see if we can. That should work. This actually might throw an error, but well, let's see. It will throw an error because that is not supported. Anyway, that's fine. But what I'm trying to get at here is that line, what you'd have done is printed what's the type of A is. Since we can't print it, might as well guess it. What do you think will be the type of A and type of B, type of C? Okay, let's go one by one. Type of A, integer. Yes, that's correct. Type of B, integer reference. No, it will be integer. Type of C, yes, integer. Again, T will also be integer. Now here's the thing. That's the thing about auto. Auto uh, from the right hand side will infer types, yes, but it ignores references and constants. Okay. It doesn't take constants, pointers, reference, anything. Okay. But if I write it this way, that's actually by design. Hence, we have decal types to infer from A. Yeah. So let's say I write or uh, uh, I'll change the name later to so that I don't give the answer away. I'll call it variable and a. Okay. Then what do you think will be the data type of it? Sorry, the variable. So here, when I was asking about data type, I was asking about the data type of auto these variables. I will mention this. Okay. So these are the data types of here it is of A, of B, of C, of D. Basically, what we're saying is uh, yeah, basically what you're saying is what is the data type of each of these variables? So what we declared, we have something to the left side of each variable. That's fine. Now the thing is, because of that, we know its data type. So D is data type is constant integer reference, constant integer C is constant integer, B is integer reference, A is integer. That's fine. With auto, it takes the basic data type. It ignores the references, it ignores the constants. So all of these data types, auto A, auto B, auto C, auto D will be integers. Okay. But what if I have auto reference var, the variable name, equal to A? So in this case, what will be the data type of var? Uh, Slight correction, it won't be var reference, it will be integer reference. So because A is an integer, still an integer, and for var, the left-hand side has a reference with auto. Auto will infer it to be integer, and then variable, the var variable. Yeah, right. So now the var itself will become the data type which is to left of it, which is auto reference, where auto is integer. So var becomes integer reference. Okay. I hope this is clear. So it's not that auto cannot, matlab, it's not that we can't have variables as references without auto. We can. We have to just explicitly specify it. And taking all these examples, the reason to do is to actually understand how, in each case, your keyword auto works. Okay, it's important to be careful of it. So what I'll write this auto, this virus is, maybe well, maybe I'll leave it. That's okay. Let's write const auto ampersand var2 equals to a. So here again, yes. So here again, I created var2, okay, from a. So what will be the data type? So slight correction again. It won't be constant integer, it will be constant integer reference. Okay, because yeah, reference here. All right. Now let's take example with decal types. Okay, and I'll call it a decal as a. Okay. Similarly, write for each of them. B, 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 D. Yeah, no. For if it would have been auto, then yes, but this is decal type. So, uh, sorry for that. G, D, D. Yeah. So A will, sorry, A decal will be integer because that's the data type of A. But yes, that's correct. It will be actually similar to this data type because decal type actually infer the actual data type. So P decal will have the data type as integer as the whatever the data type of B is. Okay. Similarly, as an integer reference, C decal will have the data type as const integer. Okay. And then D decal will have the data type as const integer reference. Okay. Now this clears it. With auto, it will always be integer in all these cases. For the same case, when you take it as with decal type, they will retain their original data type. You can think of it like this. There is inbuilt data types, integers, okay, like integers, pointer, floats, doubles, and so on. There are more qualifiers to it. So const is more qualifier, saying something which you are referring to is constant, cannot be changed. That could be ampersand, okay, you can think of this way, which means it's a reference. If it's a pointer, then it will be a pointer here. It's a pointer. Okay. Typecasting happening. Oh, that's the thing. There is no typecasting here. Decal type essentially infers the data type from A and sort of like it replaces integer here. You can think that way. It's like a macro. Okay. It infers the data type of A, replaces it with macro. We replace it with like sort of like integer. Here the same integer reference, const integer reference. It's not a macro, but you can think of it like it behaves like a macro. If A was signed in, then only it will happen. Um, you can have typecasting, yes. So right, let's say here this is an integer, so it's not an issue. Yes, that's correct. But let's say I have unsigned int. Okay, let's say I have unsigned int e to be 10, let's say. And then I use decal type on e, declare variable f, and store -10 to it. Okay, let's see what happens. So what actually happened here is e had 10, okay, which is unsigned int. So decal type of e is unsigned int, okay. But what I'm trying to store is -10. So f will be unsigned int, no question about it. But then there will be typecasting happening where what we're trying to store as -10 will now be stored as unsigned int. Let's print and see what it actually stored. Maybe it will not store never fully. So let's print it and see. Yeah. So that's what happened. What happens in with unsigned int is there is a with integers, this is not the behavior. So when you try to go out of bounds, so there is a limit. So let's say integer, when I say it is 32-bit integers. So there is a limit on the negative end and the limit on the positive end. Okay. When you try to go out of bounds, the actual behavior is undefined behavior. Okay. But with unsigned integers, the behavior is sort of defined as in it wraps around. So let's say you had a number, unsigned integer as a, let's say, which had the value 1. Let's say you do a minus 2 and store it as unsigned integer. Okay. Then what happens is it goes to minus 0. First is minus 1. So to minus 1 from 1, minus 1 will be 0. Then when you subtract 1 again, it wraps back to the highest value. Okay. Sort of like that's what happened. When you try to store a negative number, it's sort of like stored a very large number, as in where it corresponds to in the wrapping. Sort of like that. You can think that way. So 4.2 billion or something, that is the highest number, 32-bit number, unsigned integer can store. Okay. You can look this up. It's about 4.2 billion. That value in sort of like corresponds to a negative number. Okay. A negative number in unsigned integer corresponds to this large number. Yeah, it is defined. Yes. This is the behavior in unsigned integers, but this wrapping around behavior is not defined in integers. But in unsigned, yes, it is defined. Okay. So yes, implicit casting can happen unless we do explicitly. Implicit casting did happen here. And using decal type, auto, all that, you can have implicit casting. Yes. No, sometimes it's not an error actually. It's the programmer's fault trying to set a negative number to unsigned integer, which one should not do. So yeah. Okay. Right. I will uh, actually this has led to some funny bugs. Okay. One example on top of my mind comes to there's a video game, as it's a computer game called Civilization, where due to this unsigned integer error, uh, so they used to store something called aggressiveness, how aggressive a civilization or a nation is. As in, you're playing the game, there are a lot of players, right? As in, they could be NPCs, non-playable characters, and you are one of the user uh, playing the game. The other, yeah. So um, they used to store this in unsigned integer, the sort of like the aggressiveness. And what happened is a certain nation, I won't name it, certain nation's character especially is known to be quite non-violent. So the value also is already less, and they due to some characteristics or mechanics of the game. Okay, the yeah, it is, yes. So yeah, so the value kept decreasing, and when it reached 0 and again decreased, it wrapped around. Okay, and the value became one of the largest, right, possible. So that character became the most violent. So this is another example of the wrapping around behavior of unsigned integers. Okay. Yep. You got it right. Yes. That's the character. All right. As an additional example, I'll cover another just a data structure called initialize list. Mm, let's include that file first. Initializer. I think it's underscore. Yes, underscore. List. Okay. And then include file string. So let's say I have an init list. Okay. Which looks something like this. It could have some values like 5, 4, 9, 2, 15, so on. Again, here a very nice thing about auto comes in. I just can put auto. This is a defined data type in C++. So because I've included an initializer list, this is an initializer list. It's like a collection of some values. You can put curly braces, and then it knows what the data type is. You can just put auto and not worry about it. The actual this init list, okay, the data type looks something like this. Standard initializer list, and has to be templatized integer. So because all of these are integers, it knows to be integer and then auto takes the. Another nice example. I don't need to worry about what this data type actually looks like. I can start using it automatically. Let the compiler figure it out. Okay. So another small thing. So I can do this. So it knows the data type. It's an integer. Okay. Then again, I have auto, which is this way. I do it this way. This is also valid code where you are sort of like using B as a object, okay, of data type some auto, okay. But according to the input, it sort of acts like a constructor. And here again, it is an integer. Similarly, you can do this, but instead of those braces, you can just do curly braces. Okay, be careful. Here it is an initializer list. I'll put that. Okay. All right. Yeah. Again, so there is another way you can declare variables. So usually we set it using equal to, right? So using equal to, one is an integer. So A knows A will be an integer. So auto knows that. As in using auto, compiler knows that it will be an integer. That's fine. There is another way of initializing numbers. So you can also do this. You can do that. But let's say I want to use auto. The same A equal to I or uh, B equal to I, you can use brackets to initialize. Think of it like classes. Okay. The class is the integer itself. Okay. And depending on the input, it decides the data type that is taken by the auto. Yes, you can do integer A10. Yes, you can do that. That's a valid code. Here in the case that you have written, the object, okay, I'm not talking in terms of classes and object. The object is A, the class is integer. Even inbuilt data types can sort of, you can think like classes in C++. So it allows you to construct an object A, which this is the initialization part, which takes 10 as the parameter. So it calls its constructor, okay, sets it to 10, which is A itself. I mean, that's what we are saying. Okay. So that's a valid code. Similarly, you can do B of 1, but you have to actually specify the data type. Okay. You have to declare the data type. I can put auto because it knows what the data type will be. Okay. But now I'm making it a little more complicated. But instead of using brackets that we normally do for constructors and objects and such, what if I use this curly braces? Then it becomes an initializer list. Okay. So C is an initializer list. To show this example, I defined what an initializer list is and then went through all this. Okay. All right. That's yeah. Any questions? I think I wanted to cover these things. I did. Okay, that's all. Okay. You can also use auto C T1, T2 as a list. Um, that should be fine. Yes. Yeah. Now, but you have to give what the T1 and T2 are, as in they should be of the same type and the same values. I mean, not the same values. They should be of the same type because initializer list needs the list to be of all of them to be the same type. It's not like Python where you can have different data types inside a list. Okay. Yeah, because if you see here, the initializer list takes a template parameter. So it ensures that all the elements inside the initializer list will be of that template size. So the curly braces mean list, yes. And those that singular bracket mean any singular data type. Yes, that's true, but I mean that's what it seems like here, yes. But one thing to remember is that these small brackets are for constructors. Okay. Again, technically speaking, this is also a sort of like a constructor happening, situation happening. But depending on what braces, type of braces you use, your data type will change. Is what I'm trying to say. Yes, in this example where B is just a single variable, taking multiple inputs will probably throw an error. We can actually check that. Here it probably doesn't make any sense to do this, but let's uh try and see. It should throw an error because a single variable doesn't know what to do with two variables. But we have this, then it's all good. Yeah, because it can take one variable, set it to B. But for C, we can do this. I think should be okay. Each has a list, multiple autos, it doesn't take. Yeah, it doesn't know. We have to use the equal to then in that case. But still, nonetheless, one value it is okay. Yeah, okay. If you use list integer instead of auto, then what will happen in line 9? You can use it. That is a valid. So essentially, instead of auto, we are putting it as a list. Yes. It's just a list with single value. That should be okay. Let's see. Yeah. So it's C is a list with single value and give multiple input. Oh yeah, let's try that. It's a good suggestion. That's perfectly valid. Yeah. Yeah, yes, exactly. Yes. You have to be careful what auto can do or cannot do. Yeah. Yeah, here you can. Yes, that's correct. Because the data type of C is sort of known, like, okay, no, we can't, here we can't add it, because it's a bracket. If we had equal to, then we can, as in here we can. That's what we saw here. Adding more parameters to it with brackets, it doesn't know what to do with it. Here we can add auto. Yeah. Inside template, you cannot add auto. I mean, you can try it. Normally, it should be known at comparison time, but let's see. Uh, yeah, let's try this. I've never tried this actually. Hmm. Let's see. Might work. Okay, it doesn't. You can't add auto inside template parameters. Yeah, that's it. It's not allowed. Mm, yeah. It accepts templates, which we normally represent using capital T. Yes. Yeah. Yeah. Okay. Next class, we can cover the day 12. So there will be one extra session. So next Tuesday will be the last class. That will be the week 12. But I'll take another extra class on the next Wednesday, so the day after Tuesday. So Tuesday will have the 12th week class, and there'll be 13th week on extra class on Wednesday. So these two classes I'll mostly try to cover. I mean, the next class will cover lambda expressions and yeah. So two more classes, lambda expressions and smart pointers. And if time permits, I'll sort of revise the whole topics that we have seen so far. Yeah. So because I discuss doubts and also, I mean, I cover some topics, I clear, give examples and also clear doubts. It's difficult to cover all the topics, but at least I hope that most of the topics that I have covered are the most are relevant, and at least the important ones I have covered. Um, Other topics you can always go through the lectures and all to understand. But yeah, the plan is next two classes, I'll try to cover lambda expressions and smart filters. The two very important concepts in modern C++. Yeah. So far we covered all the templates, input, output, and all. But yeah. Thank you. Thank you. Yeah. Sure. Actually, if you have questions like that, you can definitely ask. You can put it in the chat. I'm pretty sure I understand what is happening there. It's probably three only, but seems like it is more than that. So I'll go. I mean, I probably don't need to see the code also. I'll just say. So if you see a for loop, we have some integer, let's say I equals to 0, I less than my favorite number, let's say 7, then I plus plus. So you can see there are three clauses separated by semicolons. So technically speaking, you can have more things inside here. So you can actually do this. I'm not sure. I mean, you might have to see the syntax, but I'm just giving a rough idea. You can have j equals 0, I less than 7, and j less than, let's say, another value 11, I plus plus, j plus plus. So yes, it looks like a lot of parameters are there and everything, but the point is that they are different sections and separated by semicolons. So this portion is the initialization. This is the conditional for check. And this is what happens every iteration. You can have plus plus, you can have j plus equal to 5 or 4, anything, and so on. This is also a valid for loop. You might have to check about these commas a bit, like as to how will the exact syntax be, but more or less this is the idea. Yeah. No, actually, we're not. So if you think about it, it's a single loop still. Okay. Now, how long it will run depends on the condition. Both start at 0. Yes. But it will actually run till 7. Why? Because, okay, not here I made it a bit more complicated. Let's say it was originally plus plus. So increment of both of them happen in units of 1. But but I will reach 7 first, then j will reach 11. So this loop will run till the size, like 7 times, as in the size of whatever the limit on 7 is. And all the computations in that 7 iterations will be done with corresponding values of I and j. That's it. So it is still O of n. If I say n is, it's actually O of less of n1 and n2, where n1 is the size of I, n2 is the size of j. And because I put an and here, it won't, right? This condition says my loop will run till this portion inside the two semicolons is satisfied. Means this condition is satisfied until I is less than 7. Once I goes out of 7, even if j isn't, because of the AND operation, it will become false. Yes, that's correct. You can actually put an OR. So then even if this is not true anymore, at least j will still go till 11. And then when both become false, the loop terminates. Yeah. Here's the nice thing. You can use this parallel lines as for or you can actually write or C++, modern C++ at least supports both. You can actually write and also the explicitly to imply that you mean and here. That is also fine. Like in Python wonders, or and. Yeah. I hope this was what we saw in 5 parameters that you mentioned. Yeah. So here, let's say I call it N1, N2. Complexity will be O of min of N1 and 2. Yeah, correct. That's correct. The concept is that for loop has 3 sections separated by semicolons. Very important. First section is essentially an initialization. Okay. You can actually do this also. Let's say declare variable k, integer k, that is fine, and set it to 0. Sorry, k equal to 0 here. I think one you have declared because you have not declared j, so maybe you have declared it here like this. But you can absolutely set it to 0 and not declare because it's already declared inside the loop. This is perfectly valid. Have a condition, second portion, and then some conditions on I and j. You possibly, if you don't want any loop iteration to like do anything for k, that is also okay. Maybe it happens inside the loop, or maybe it doesn't. That's also, it depends on the logic. It's fine. Yeah. Prime series in O of n. Um, what do you mean by prime series? As in print, go through 1 to n and print all the prime numbers. Is that what you're saying? Okay. Well, not exactly, right? I mean, how do you uh, I see what you're saying, though. So I have two loops. One is to check one goes through 1 to n. Second goes to um, um, yeah, 2 to square root of n, let's say. You can try it out, yes. So first loop goes through, let's say 1 to n is some number. You want to print all the prime numbers inside. There's a second, instead of second loop, you have second variable j, which runs till 1, j till n, j till I, or it runs till, I mean, that actually might require another loop. Hmm. One has to be, one can try it. Yeah. Maybe it requires a condition which can be evaluated from a constant, because here j less than n is known. If j varies, yeah, I mean, I want us to try it out. Maybe it can work. Yeah, try it out. What then you can do is, to make it efficient, have a loop as an I, which runs from 1 to n. The second j runs till 1 till square root of n, or square root of I, because I is going, so square root of I, yeah. Convert to an integer and then run your loop till that. And then check if I is divisible by any values of j. That is one way. Hmm. All right, that's a good one. Yeah. All right, awesome. Thank you so much. I hope you enjoy the class as much as I could. So yeah, happy coding. Yeah, I understand. Um, yeah, but that's the thing. NPTEL sort of allows me to do only that many classes. So yeah, the week was supposed to be 12, like the actual course is of 12 weeks. So 12 TS sessions in that sense. Yeah, right. Okay. I actually replied to your uh, comment, I think in the forum. I think you can find it there. Did you get a chance? I don't recall, but I think I replied to your question inside the forum. I think I pasted the link. But was it the playlist? I don't recall. In any case, I can paste it here. That's absolutely okay. About the report, it's um, definitely useful to have this. So why not? Oh yeah, absolutely. It's good to the best way to practice code is actually doing it. So once you actually write and code it, like run it, then only you understand. So I pasted the drive link. This should you should be able to access the repo. Um, the playlist also, maybe I'll just share again. I don't know how the rules for this happen or anything, but I guess anyway it's public, so I guess that's fine. Um, Let me see. So the sessions, yeah. So the sessions that I am teaching this time, they should be in a playlist, which is so this is the January, right? January 25. Okay, good. Okay, this is the one. And this is the playlist with all the sessions that I've taken so far. I'll add today's sessions also, and the codes also I'll update in the repo. Yeah, sure. Just be careful. Some of them might be just comments by me with not proper syntax, so you might actually run into errors. But again, it's a nice practice to figure out. I mostly comment those stuff, but just be aware. Yeah, which are more like just to give an idea of what the syntax or the pseudocode looks like, not actual proper code. But yeah, um, okay. Some right. Yeah, good. That's the spirit. Uh, so the compile is our friend, as in it whatever whenever it throws errors, it is actually helping us to understand our code better and improve it. So that's how we should take it. Yes. Yes. Awesome. Thank you. Thank you so much. Okay. Good night. And yeah, it's good that you're practicing. So be at it. And yeah, if you have any questions, you can ask again on next classes also. And see you tomorrow. See you next class.